Oxidation-reduction reactions. In these reactions, we have electrons being transferred from one reactant to the other. They're also called redox for reduction, oxidation, I guess because ox-red sounded stupid. It always reminds me of red box, though. Redox, red box. It's just missing a B. Makes me want to go watch a movie. So redox reactions, oxidation-reduction reactions, two names for exactly the same thing. Many of these involve something reacting with oxygen. So iron reacting with oxygen, octane reacting with oxygen, hydrogen reacting with oxygen. These are all oxidation-reduction reactions. And this reacting with oxygen is where they got their name, because oxygen, they're being oxidized, they're getting oxygen. Here we have a balloon filled with hydrogen and oxygen, and you light a match to it, and you start this oxidation-reduction reaction that generates a lot of energy, and it forms water.
What's the definition of it again? Oh, okay.
You can also have an oxidation-reduction reaction that does not involve oxygen. When it has oxygen in it, it's called a combustion reaction. When sodium and chloride react, they form sodium chloride. So you have two elements, and then you end up with an ionic compound. The sodium is an atom here, and it's an ion there. How does sodium become an Na+ ion? It loses an electron, right? How does chlorine go from being Cl2 with no charge to being Cl-? It gains an electron. So there's a transfer of electrons from the sodium atoms to the chlorine atoms, and that's an oxidation-reduction reaction. Why does
one without oxygen be an oxygen-reduction reaction?
Well, a lot of the names that we have started out from an observation. They observed that these sorts of things happened when they involved oxygen. Then when we learned about electrons and actually what was going on, we realized, okay, this is a general category that applies to more things.
Should have renamed that category.
Well, yeah, maybe they should have renamed it, but so many people were already familiar with that word. You know, it's like deciding to call Texas something else. It's going to be hard.
What exactly is like the definition now of an oxidation-reduction?
An oxidation-reduction reaction involves the transfer of electrons from one substance to another. It often involves oxygen, but it doesn't have to. So let's look at these two. Here we've got sodium reacting with oxygen, and this forms an ionic compound. And sodium reacting with chlorine, and this forms an ionic compound. Both of these are a metal reacting with a nonmetal. And that is very typical of oxidation-reduction reactions, a metal reacting with a nonmetal. It just, the nonmetal doesn't have to be oxygen. It could be chlorine or something else. So when we look at what's going on here, the sodium atom is becoming sodium ion. The oxygen atoms in this molecule are becoming oxygen ions. Isn't that a mess to look at? Yeah, that's why we don't write charges in our chemical formulas for compounds, because it's just really messy. We wrote them there to point out that now these are ions with charges. Here are the sodium atoms in the chlorine molecules. There was a transfer of electrons, and they became ions. So to convert a free element into an ion, atoms have to gain or lose electrons. If one atom loses an electron, another one has to gain it. So there's no electron bank. There's no electron shelter where you can just go drop off unwanted electrons. You have to find someone to take them. So if one atom loses an electron, there has to be another one that takes that electron. So they always go together. It's a transfer. We say that atoms that lose electrons are being oxidized. Atoms that gain electrons are being reduced. So the little it's not even really a phrase. Oil rig helps us to remember. Oxidation is loss of electrons. So oxidation is loss of electrons. Reduction, R-I-G, oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. And that's one of those things that, unless you use it all the time, it's really hard to remember which one. I still have to pause in my head and think, oxidation is loss, is this losing an electron? And I have to figure it out every single stinking time. Yes?
This is the concept behind glycolysis in the body, right?
Yes, oxidation is involved in glycolysis in the body. There's a lot of oxidation reduction that occurs in biological reactions. It's really, really important. So when sodium and chlorine react and form ions, there's a complete transfer of electrons. And that's easier to understand. It doesn't have to be a complete transfer. We can just have a partial transfer. So when hydrogen and chlorine form hydrogen chloride gas, this is not an ionic compound. There's not a transfer of electrons, but there is a shift, a partial transfer, if you will. So they're now unevenly shared. The chlorine is kind of hogging the electrons, and the hydrogen is a little bit shortchanged, but it hasn't been completely transferred. Now, when you stick hydrogen chloride in water, then that transfer gets completed, and that's how it forms the two ions. But just in pure form, it will not happen. So what we see here is that we have an increase in electron density for chlorine and a reduction or a decrease in electron density for oxidate. Start over. We have an increase of electron density for chlorine. Oxidation is loss, reduction is gain. So the chlorine is being reduced because it has a gain of electrons. It's just a partial gain, but it's an increase. And the hydrogen is oxidized because it's experiencing a decrease in electron density. So when we have these non-metal reactions occurring, like between hydrogen and chlorine, it's a lot harder to identify what's being oxidized and what's being reduced. And so chemists came up with something called oxidation states or oxidation numbers. It's an artificial technique to help us figure out what's being oxidized and what's being reduced. So note this statement. Oxidation states are not ion charges. They're imaginary charges assigned based on a set of rules. Ion charges are real and measurable. Oxidation states are not real. They are not measurable. They're just a trick to help us figure out what's going on. What really gets confusing is that many times the oxidation state is the same number as the ion charge. And so that's why people get them confused. So here are the rules for assigning oxidation states. And these are in order of priority. So first of all, any free elements are going to have an oxidation state of 0. So sodium all by itself, oxidation state is 0. Cl2, okay, that's a molecule, but it's an element. It's not a compound. Oxidation state for those chlorines is 0. The next rule is that monatomic ions have an oxidation state equal to their charge. So you've got sodium ion, you've got chloride ion. Sodium ion has a +1 charge. Its oxidation state is the same number as its ionic charge. But oxidation states are not ion charges. The chloride is -1. If we have a compound, the sum of the oxidation states of all the atoms have to add up to 0. So in this compound, NaCl, the +1 oxidation state of sodium and the -1 of chlorine add up to 0. If we have a neutral molecule, the oxidation states add up to 0. If we have a polyatomic ion, the oxidation states of everything in it add up to the charge. So, for example, in nitrate ion, the oxidation states for nitrogen and these 3 oxygens have to add up to equal the -1 charge. In this example, nitrogen is +5 and oxygen is -2. There's 3 oxygens, that's a total of -6, and there's 1 nitrogen at +5, and so it adds up to -1. In compounds, metals are always going to have positive oxidation states. Yes?
So is it easier for that one to figure out the, since we know like the charge of oxygen is 2 minus, figure that out first, and then take.
Yeah, and then we figure out the nitrogen based on the oxygen and the overall charge. And that part is coming at the very end. In compounds, metals are always positive oxidation states, just like they have positive ionic charges. The group metals are +1. The group 2 metals are always +2. The nonmetals, they're going to go according to this table, okay? So fluorine has the highest priority. Fluorine gets to be -1. Hydrogen gets to be +2. Why did I say 2? Hydrogen gets to be +1. Oxygen gets to be -2. And then they go in reverse order here, group 7, group 6, group 5. So these are -1, -2, -3. These oxidation states are the same value as the ionic charges that these elements like to form. Yeah.
So isn't this just the same as like valence electrons?
It's similar to valence electrons, and yet it isn't. Because what we'll see is that like nitrogen ends up having all kinds of different oxidation states, when as an ion it's always -3. Yes?
Can you explain rules 1 and 2, like the free elements versus monatomic ions? Like why would free element of sodium be 0 and then monatomic +1?
So
Will it
the
tell you?
rules are helpful, but they're kind of confusing too. So I'll try to give you the big picture. So the big picture is that oxidation state often correlates with ionic charge. So sodium element has no charge. Its oxidation state is 0 also. Sodium ions have a +1 charge. The oxidation state is +1. The reason we have to do this is because in compounds like ammonia or sugar, where you just have a bunch of nonmetals, there's no ions, how do you decide which one has the larger share of the electrons? And that's why we need these rules.
Why does nitrogen have 5?
Well, nitrogen can be +5, it's sometimes +3 or +4, it can vary. And the exact reasons why are more complicated. So let's do some examples, and hopefully, yeah.
So you know, you said that the oxidation state doesn't reflect at all the ionic charge?
No, I said that the ionic state, the ionic charge and the oxidation state are not the same thing. They're sometimes the same number, but oxidation state is a different concept than ionic charge.
So that's why then like the oxidation state of ammonia is then 3 minus, but the ionic charge overall is +1.
Yeah, so this here, ammonia is a neutral molecule. It doesn't have ions, it has covalent bonds. And so, yeah, nitrogen gets to be an oxidation state of -3 in this compound, but it doesn't actually have a charge of -3.
So when you do like the, you told us last semester like 765. So like we're trying to find oxidation states. So if you had like HF and then you're trying to find the oxidation state, you would find have to write it down.
Yeah. So
It's confusing.
I think what she's referring to is, I mean, how do you remember the order here? FHO, that reminds me of pho, the Asian noodles, right? Pho. So FHO 765. I can remember that. It should be PHO, but it's close enough. It makes the F sound. So let's hold the questions for a minute, and we'll get into some examples. You can have fractional oxidation states. We write the sign before the number for oxidation states and after the number for ionic charges to help distinguish between them. So what does that mean? Well, let's look at nitrogen. Let's think of the nitride ion. When I'm writing the ionic charge, I write the sign after the number because we don't want that to look like a math exponent. But when I say that nitrogen has a minus 3, I almost did it backwards. Nitrogen has a minus 3 oxidation state. Because ionic charges and oxidation states are not exactly the same thing. What's very confusing is sometimes it's the same number, right? But the fact that it's often the same number also makes it much easier to figure out what the oxidation state is. Because if you don't remember any of the rules, go with trying oxidation state is the same number as the ionic charge, and that works most of the time. Here's examples. So here we have Cr. That's an element, right? What's the oxidation state for an element? 0, which is the same as the charge that it has, which is 0. So the oxidation state is 0. How about chromium 3+ ion? Guessing 3+, yeah. So the oxidation state is +3. And you're not going to lose points because if you wrote 3+ instead of +3. Okay? If you just wrote 3, that would probably be okay because you didn't write -3. Let's look at CCl4. Okay, now we have two different elements. And they're both nonmetals. This isn't an ionic compound, so we can't do anything with charges. We have to use the Pho 765 rules. So there's no fluorine, there's no hydrogen, there's no oxygen. Next comes column 7. Chlorine is in column 7. If chlorine was an ion, what charge would it have? -1. So the chlorine here has an oxidation state of -1 because it's got priority over carbon, which is in group 4 and doesn't even show up in the list. So we've got 4 chlorines, and they have an oxidation number of -1 each. All the oxidation numbers for CCl4 have to add up to 0.
And why 0?
Because the charge on this compound is 0. It's not an ion. So if we've got 4 that are -1 and we've got this 1, what's the oxidation state have to be? +4. Any questions?
So after that, would you say that the electrons spend more time on the carbon or the chlorine?
You'd say that the electrons are spending more time on the chlorine.
Because it's negative?
Mm-hmm. It has a negative oxidation state, so it is got a larger proportion of the electrons than the carbon does. There's an imbalance.
How did you get 4?
I got 4 because I know that I've got 4 with a -1 oxidation state, and these have to add up to 0. So I need to figure out what X is. X is the carbon. Has to be 4. Any other questions? Let's look at this one. SRBr2. Strontium. This is an ionic compound, isn't it? Strontium's in group 2. The rules say that the group 2 metals are always +2 ionic, +2 oxidation state.
Wait, so going back to C, what would be the oxidation state?
The oxidation state on carbon is +4. There's no charges.
For C, it's just +4.
Yeah, for carbon, carbon has an oxidation state of +4. If we made this into an ionic compound, those are what the charges would be, but it's not an ionic compound.
So why are we ignoring the chlorine then?
We're not ignoring the chlorine. The chlorine is -1. If there was no chlorine in there, then the carbon would be 0, because it would be alone. This is confusing. So strontium's +2, so then the bromines have to be what? -1. Because there's 2 bromines. The strontium gets to be +2. There's 2 bromines. These oxidation states have to add up to 0. And so the bromines must be -1. It's very, very, it's like dangerously similar to ionic charges, isn't it? So you can think of it as ionic charges as long as you keep in the back of your mind, but it isn't. Yes?
So a neutral molecule in the compound is 0, but a polyatomic ion has to equal the ion.
If it's an ion, the total of the oxidation states has to equal the charge on the ion. Neutral compounds have overall charge of 0, and so the oxidation states have to add up to 0. Let's look at SO3. What kind of a compound is that? Non-ionic. It's molecular. It's got 2 nonmetals. So we got to do Fe765. So fluorine, no. Hydrogen, no. Oxygen. Oxygen wants to be what? Oxygen would like to be -2, the same as the charge it takes when it forms an ion. It's not an ion here, but it would like to be, perhaps. So it gets to be -2. There's 3 -2s. That's -6. So what's the state of sulfur? +6. It's like learning to play hearts or something. How about NO3-? Yeah, oxygen wins again. Oxygen gets to be -2. There's 3 -2s, that's -6. Overall, we need to have a -1 charge. So the nitrogen is what? +5. Does nitrogen form a +5 ion? No, it doesn't. It's okay. This is made up. You thoroughly confused yet?
So for E, so because of the rules, oxygen is -2, and then multiply that by 3, which is -6.
Yep, so we've got 3 oxygens, and they each have an oxidation state of -2.
And it has to add up to 0.
And it has to add up to 0, so the one that we're missing goes in there.
Okay.
Okay? Your brain's full? We'll save the rest of this oxidation state business for next week.